having me. So yeah, I will follow on these lovely talks and talk to you about Sentinel-3 for sea ice monitoring. So we're moving from glaciers and land ice and looking at sea ice. I'm Michel Tsamados. I'm associate professor at UCL in the Department of Earth Sciences. So really, this talk is an homage and credit to an amazing mission, or two amazing missions, called Sentinel-3 from the Copernicus program. So let me see if I can actually go to the next slide. Okay, so the other speakers did a great job in introducing the concept of Arctic amplification, but I'm going to take you again and zoom in the Arctic Ocean. The Arctic Ocean is this frozen ocean around the North Pole, really. And so here I did a little schematic showing to you the maximum extent of the sea ice at the end of the winter, and it's about 14 million square kilometers. And if you look at the end of the summer, you have a shrink, the sea ice shrinks and melts, and we have about 4 million square kilometers. So this is happening every year. There's a kind of breathing pattern. The fact that the sea ice is declining, you might have heard about it, and is primarily driven by warming of the Arctic temperatures. They are warming much faster than the rest of the planet, up to 4 times faster. This is what is referred to as Arctic amplification. Actually, if you compare the last 20 years from 1990 to 2010, actually this 20-year difference in period, you have regions in the Arctic that have warmed by up to 5 degrees on a yearly average. So this is unheard of, and it's the only place on Earth really that is so intensely warming. And so this results in retreat of sea ice. Here you see regions that have lost up to half of the coverage, and places like north of Russia, Murmansk, and so on might have no more sea ice now or in the winter, which is totally changing the landscape, the local landscape. So, but the extent is a kind of simplistic view of the Arctic, right? It's a white map, a 2D map of where there is ice or no ice. But actually, what also matters is how thick this ice is. So our team and our university for many years now have been pioneers, and also Legos, actually, the group of Etienne, in the past, have been pioneers in monitoring the thickness of the ice from satellites. And so today I will cover also that it's a tool called altimetry. So we use altimetry to measure the thickness of the ice. So this is a little schematic showing to you where is the thick ice. So orange is the thickest ice remaining, and it's about 3-4 meters north of Greenland, north of the Canadian Arctic. The remaining ice can be very thin, just a few tens of centimeters in the Russian sector, typically. So it's important to monitor the thickness, not just the extent. That's the message I want to say. Now, if we want to predict when the sea ice will disappear, I was working on sea ice since the 2010, and when I first worked on sea ice, there was this kind of graphic of the declining sea ice extent in September. And so people were very, very worried, and they were doing some simple extrapolation of this decline, rapid decline. And some people had predicted that the ice will disappear by now. So this red line is 1 million square kilometer. And if it crosses that line, we tend to say the sea ice has disappeared. And I was worried as well. But actually, in the last 10 years, something has happened, which is called, chaotic, the chaotic nature of the climate. There are many timescales, and one of them is decadal variability. And so the sea ice has actually slowed down in terms of extent, in declining in extent in the last 15 years. This is something that was documented and published earlier this year. But actually, this is not a happy story, really. The sea ice is melting rapidly still. And so if you look at the volume, the sea ice continues to rapidly decline. So don't take that as a happy story. And also, this is predicted to continue to decline in the future. But yeah, let me tell you what I will talk about. Sentinel-3. And again, Sentinel-3 is an amazing pair of satellites, A and B. They've been launched almost 10 years ago, the first one, and 7 years ago, the second one. And so there are different modes of operation for the altimetry part of this satellite. SAR mode is really the legacy of CryoSat-2. It's a high-resolution altimetry mode that allows you to measure the elevation within a narrow localization. So I will tell you about these two satellites and how we came about to use them and what kind of results we found with them. The other amazing thing with Sentinel-3, again, a Copernicus mission really, is that there is many instruments on board. So the synergy of data that that you can collect with this pair of satellites is amazing. So here I will only have time to cover optical and altimetry, but I have a few slides on passive microwave and thermal, which are the two other instruments you have on board Sentinel-3. But if you have questions, I'm happy to take on the other topics as well. So I'll start with optical, and there is an instrument called OLCI. And so with this instrument, I'll play you a little video. If you follow the satellite, you can see really the surface of if there are no clouds, you can see the surface of the sea ice in that case. Here we're crossing the Alaska from the Bering Strait to the Pacific Ocean. And we see really where there is ice, when there is no ice, when there is fragmentation of ice, and we can estimate the concentration of sea ice that way. But the resolution is 300 meters, right? So we have developed new products based on that, but this remains a limit. 300 meters is high resolution, but it's also low, can also be seen as a low resolution if you want to do, for example, navigation or very high resolution needs are required. So what we proposed a few years back, 2 years ago, was to try this technique in the area of machine learning, in the age of machine learning, to try and super resolve these Sentinel-3 images. So the bottom pixelated image here is a Sentinel-3 image at 300 meter pixel resolution, and the top is a Sentinel-2 collocated image at 10 meter resolution. So a huge factor of enhancement, a factor almost 30 by 30,000 increase in resolution. So the challenge we asked ourselves is, if we train with hundreds of thousands of images collocated between Sentinel-3 and Sentinel-2, could we use what is called generative adversarial networks to create high-resolution images, invent essentially an image that is of the Sentinel-2 type? And so we tried that, and we had some success with mountains in particular, so perhaps something Etienne and Andrea could be interested in. We were able to take a pixelated image and invent those kind of images. This worked quite well, but it wasn't working so well for sea ice until this year, when we moved to diffusion models. And it's a kind of latest flavor of kind of machine learning models for generative approaches. And we were able now to really turn a pixelated image, as you see on the top, to something look like the truth, which is the middle row. In the bottom, we made a prediction from the pixelated image of Sentinel-3. And so we were very happy to see this preliminary result. So this is in preparation at the moment. So you can really, perhaps you don't see the exact truth, but you see something that looks very realistic and might be very important for models, for applications of all kinds. So that's an interesting example of optical applications. Now I'll move to altimetry applications. Remember, this is to measure the thickness, the third dimension, really, elevation of the ocean or of the sea ice. And our first example is a good example, actually, because it's a synergy between optical data and altimetry. Remember that Sentinel-3 has several sensors exactly collocated. And this is amazing when you look at sea ice, because sea ice is moving very fast. Unlike, I mean, glaciers are moving faster and faster, but sea ice is moving sometimes up to 1 meter per second. So having the two instruments at the exact same time is very good for things like machine learning and training and so on. So here I give you an example of cracks. You see the black things are cracks in the ice, which is open ocean. And the two squiggly lines you see are echoes from the altimeter. So a very sharp echo will correspond to a crack or an open ocean that is very flat and reflective, while a more diffuse echo on the top is sea ice. So we're able to really classify blue dots in this line and red dots, which are sea ice and leads. And we combine that with the optical imagery to really enhance the whole coverage of our optical image in terms of classification. So this was a paper published about 2 years ago, a year ago, by Wei-Bin Chen, my PhD student. Now, altimetry is quite complex. So to really understand these squiggly lines I'm showing you on the right here, the blue lines, these are called echoes, and they are the response of the radar bouncing off the surface of the ice and coming back to the satellite, in that case, Sentinel-3. So what we were able to do with colleagues in Norway, Jack Land in particular, is to create a direct numerical simulation of these echoes for real sea ice and any topography, really. And we were happy to see that our model the bottom line, corresponds very nicely to the real echoes. So this gives us a lot of confidence that we can really understand the properties of the ice, the topography, the roughness, but also the thickness of the ice. So we're able to process a lot of data of that type to make along these tracks, measure the freeboard, the thickness of the ice. The problem is that, as you see on those plots, satellite altimetry suffers from the fact that it's a reasonably localized technique. So you have a track and you measure the elevation and the thickness just at the location of the track. So you see here, for example, the white parts are thicker ice with a freeboard of 30 centimeter wide. Blue are thinner ice. So what really people want is a map, continuous map in time and space of the whole Arctic Ocean, right? So is there a way to interpolate the data in a kind of statistically robust way to create maps such as those, but everywhere, every day? So what we propose to do is to use probabilistic machine learning, and in particular Gaussian processes, to learn the spatial and temporal correlation patterns in this data, to use them to extrapolate or interpolate the data everywhere in space and time. And so we launched a software called GPSat, and that has been very successful. And we now are able to interpolate the data everywhere in time and space. And that was published 4 years ago, actually. And so now we have this technique, we can make those maps, and you see now we have with Sentinel-3 A and B on the left, lovely map for a given day of the freeboard everywhere. If we add a third Sentinel-3, and so that was something that the European Space Agency and the European program asked us, how will we improve the map? So this is Sentinel-3C is planned for launch in the future, and so we wanted to see how much we will gain in that. So we did the kind of simulation here. And we found that the uncertainty when you add the third satellite is reduced. The map is, as you can see, it's getting bluer a little bit everywhere. So this shows to you that the synergy of satellites can also help you improve more and more the quality of your retrievals when it comes to CS thickness. So you can find out more about this in our paper last year in Nature Communications, and on the software. The algorithm is open source, GPSat, check it out. Now, the same kind of techniques, we've expanded it, and here I must admit that the maths were done by my student Wei Bin Chen and my colleague So Takao and others. But what we showed is that you can use deep learning to kind of simulate these Gaussian processes in a way that's much more effective, and also to account of the full spherical nature of the Earth. And here we did a test on ocean elevation. So as you know, the ocean has highs and lows, and some of them are eddies, circulating features of the ocean. And so the left map shows the tracks of the altimeter. And so what we set out to do was to try and interpolate again everywhere at any given place, at any given time, if we could see the topographics, highs and lows of the ocean. This is also particularly interesting when you look at sea level rise on the longer term, but these features are also changing on a kind of daily basis. So the DRF map on the top right is showing to you the latest technique we developed, and the GP method in the middle is showing what we were able to achieve before. So deep random features really enhance the resolution, and the uncertainty you can see at the bottom is comparable, but the really capturing these eddies, mesoscopic eddies, is a kind of revolution in its own right. And we continue to validate and assess the quality of this technique, but we are very happy to see those kind of results. So just to kind of wrap up, I want to again pay homage to Sentinel-3 and its multi-sensor approach, which is, again, in the age of AI, extremely useful to learn from different sensors how they speak to each other, really. And I will just tell you that all of the results I've shown are a team effort. Don't hesitate to reach out to me for questions. I hope I have questions today. I'll just say as well that because I have 30 seconds left, just to give you a little flavor of passive microwave. Passive microwave was, for us, useful to retrieve snow on sea ice thickness. So we did a lot of work with Sentinel-3 A and B on that, but also to retrieve sea ice concentration. So you can see in this movie that Sentinel-3, just by itself, can be an amazing technique to monitor the extent, this kind of 2D map I was telling you about, where there is ice and how much its concentration is. And finally, just to give you a sense of something I work less on, that there is also a thermal camera on Sentinel-3. So you can see the temperature of the surface. And this is amazing at 1 kilometer resolution. And this is amazing to detect features like open ocean or ice. So I'm going to leave it at this and come back to my summary slide. Thank you very much.
Thanks a lot, Michel, for your presentation. It was really interesting to see a presentation about the sea ice. And yeah, so for now, we have only one question. So I will display it. Can you explain a bit more of how the sea ice thickness is measured, please, especially if there is snow cover above? So I think you showed maybe one extra slides with the full figure.
Maybe I should go back to this if you can. Can you allow me to go back to this? Hang on. How do I go?
Yeah, normally you should be able to share the screen.
I share my screen.
No, you can. Yeah, you can. We will go on the slide. No worries. My bad.
Yeah. So you need to remove the question, or do I go?
No worries. It will be.
Yeah. But that's an excellent question. Yeah, maybe go one before or two before this one. Yeah, or I can do it. Yeah. So yeah, that's an excellent question. I realize I went quick on measuring thickness for the interest of time. Measuring thickness is actually, hang on, I need to go back one slide. For some reason, one more slide back. Yeah, here we go. So measuring thickness is a very challenging problem. It took 30 years in our team at UCL to achieve something that is at a very high resolution, but especially because you have snow on ice. So what we do in a nutshell, we have a radar. The radar is measuring the distance from the satellite to the top of the ice, assuming it penetrates the snow totally, which is usually kind of right. And then you measure the distance from the satellite to the blue, to the ocean, in these cracks, in these leads that I showed. And this little difference of elevation is what we call freeboard. And Archimedes, a Greek guy, showed us many thousands of years ago that an ice cube that is floating has about 90% of the ice below the level of the ocean. So you kind of calculate the total thickness from what is the amount of ice that sticks out of the ocean that you can measure from space, which is amazing because you measure of the order of 10 centimeters from 700-kilometer altitude. So it's a technological achievement, really. So yeah, that's in a nutshell, how we do it. Lost you for a second. Okay, can you hear me, Gael?
Gael is
My bad. Yeah. But no, yeah, we're just reading the question. But yeah, it's so the University of Leicester would like to know if it'd be interesting in a collaboration.
Which university? Yes is the answer, but just because I didn't.
Leicester?
Leicester, yeah, of course. Yeah, amazing, especially because they work on, Leicester is a trick. You shouldn't say Leicester, it's Leicester.
Yeah.
But it's a SLSTR is the thermal camera, the thermal data I was talking about. So that would be very, very interesting to collaborate because this is the thing I work the least on. So yeah, very happy to collaborate. Just drop me an email and we're in the same country. So I'm based in the UK as well. And that would be great.
Okay, good news. Yeah. I think your email is available on the slides also. So okay.
Yeah.
Okay. Another question: why is the uncertainty of freeboard 8 larger in coastal areas and in narrow passages higher than in the free ocean? Is the SRAL sensor nadir looking?
Sounds like it's quite technical question, but
Yeah.
I can answer. There is, in particular, for when you monitor sea surface height, when you come close to the coast and also sea ice, the footprint of the radar is quite large. It can be 300 meter a long track and a few kilometers across track. So if you interfere, if you measure ocean and then there is land on the side, a mountain or something, or even vegetation, it can affect your signal, right? So you can have a land contamination, as we say. Another issue is that, of course, for sea level measurement, there are processes that are very specific to coastal regions. So sea level rise in the coasts, which is the most important for populations, for the million of people who live, or billion of people who live in the coast and will be subjected to sea level rise. The sea level rise is different, needs to be adjusted and understood. So these are the two main reasons why there are larger uncertainties of sea surface height. Now for freeboard, it is mostly the land contamination issue. I work, for example, with Inuit people in fast ice in channels of the high Arctic in Canada. And the channels are a few kilometers wide. And so for some of these channels, it is quite hard for altimetry to work. There are, or at least radar altimetry. There are laser altimeters like ISAT2 that have a smaller footprint of the order of tens of centimeters or meters, and then you can actually use them. And there are other satellite techniques and sometimes proxies of thickness that you can try and use. But yeah, that's my short answer. It is difficult. And as you saw in my maps, the uncertainty was larger near the coast, mostly due to coastal contamination and lack of data, because you have less data.
Yeah, thanks a lot. Yeah, it's usual to have a bit of issues around the coast with the satellite data. So we have this question, could you use diffusion models above mountains, like for the sea ice, or is it not necessary or too expensive?
Yeah, good question. I'm a sea ice expert. That's why I started with sea ice. But as you saw, I did it also for mountain ranges. You can use diffusion model in different applications, right? So here it was more for optical imagery. So we were making images of mountains and things like that. Etienne showed some amazing digital elevation models. And so we are working also on digital elevation models for sea ice from diffusion models, and it works. I'd love to work with Etienne to discuss these questions. The short answer is yes. Is it too expensive? This is a good question. In the age of AI, we should be careful with not wasting resources, computational resources. Often with models, AI can be quicker at inference or at running the model, but it can take quite a lot of time to train the model. And actually, diffusion models are a special breed. They are actually also quite expensive at running, at deploying. So I think there needs to be a good budgeting of how much this is costing in terms of CO2, water resources, and so on. And we shouldn't be wasteful when we do these things. We should also consider that. So it's a very good question.
Yeah. Good. Thanks a lot. So that was the last question for your presentation. Yeah, it's the last. Thanks again for the presentation and your participation.